All right, guys, today we're going to start by looking at renewable resources, and we're going to be focusing on geothermal resources. But before we do, let's just have a quick look at renewable. Okay. So a renewable resource is a resource that can be replenished at the same rate that it is used. So this is a resource that can be replenished or replaced at the same rate. Okay, so when we're thinking about this, we're really thinking about energy at the moment. However, the renewable resources can refer to anything such as anything we use to cycle things within the earth, or it could be used for things that we use to survive, like air, food, water, etc. Renewable resources normally can be replaced within years, months, or decades, generally within a human lifespan. So we normally think of a time scale. And time scale is important. So we might think it is within years, as in the case, for example, of wheat or fish. We might think a renewable resource, for example, might be renewable within decades, as in the case of timber. Or we might think of this over even a shorter scale, or even over a scale where a resource will never run out. And we're going to think of solar energy. We might think of geothermal. Or we might think of something like wind. Okay. There are other resources, non-renewable resources, and they are replaced over geological timescales, millions and millions of years. So let's look at geothermal energy to start with. So within the syllabus, there is a dot point: decisions to invest in energy technologies that harness the Earth's internal geothermal heat are informed by environmental, economic, and political considerations. So that's what we've got to take into consideration. That's the dot point, and we need to make sure that we know that. So let's think about geothermal energy itself. Geothermal energy is geothermal comes from two words, comes from the Greek words for geo, which is earth, and therme, which is heat. So geothermal energy is basically heat from the earth. And we think of the source of this heat, there are actually three sources. Firstly, the source is radioactive decay. Of elements such as uranium, thorium, and potassium. within the Earth. As these elements break down and decay from parent into daughter isotopes, and they release heat, and that heat generates heat within the Earth. The other source it's a bit of an unusual one. It's heat remaining from the Earth's formation. So when the Earth was first formed, a great deal of heat was generated, and that does not dissipate instantly. It takes a very long time to leave. And finally, it's not really going to be helpful to us that much, but it is heat absorbed from the sun. But you notice here it's only in the upper 10 meters of the surface. Doesn't have any great deal of influence further down within the Earth. So there are three sources of energy. Radioactive decay is our primary source of all heat. All right, let's turn over. Okay, so we're now looking at the source, or we've talked about the source of geothermal heat. Now let's look at something called the geothermal gradient. So the geothermal gradient generally is known as the increase in temperature with depth within the Earth. Within the Earth. Now, normally, and this is a generalized statement, every 100 meters you go deeper, for every 100 meters depth, the temperature increases by about 3 degrees Celsius. Now, there are a few things that can change this: the location, and the geology. Surface geology, such as the types of lithosphere, the continental or oceanic crust, can have an impact on how hot it might be. It's a type of rock. And the type of plate. Now, let's take this little one here, type of rock, and we're going to refer this to a rock that we have around here, and it's called granite. So granite itself contains with it some naturally occurring radioactive elements. Radioactive elements. They are radon, uranium, and thorium. Now, if a rock has some high amount, perhaps, of one of these radioactive elements, then there is a chance that this granite will become hotter. hotter than other rocks. So that there is a possibility of a granite that has high amounts of these radioactive minerals is hotter and then could be used to heat something else. Okay, so we've now talked about granite, and granite being a rock that has a potential to heat up and be used as a geothermal energy source. So let's say, for example, here is a little section of the earth, and here's the house on the surface. And here is our granite down here. I'll just put that there. And it is our hot granite. How do we bring this heat to the surface? What would be the mechanism to bring this heat that's down here up to the surface for us to use? Well, the answer is with water. Water is our mechanism for moving heat. This happens in nature a great deal with weather systems and climate systems, but water will retain heat energy for longer than air will. It also can be transported to the surface. And one other thing about water is that when it's brought to the surface, it's often so hot it will produce steam. And steam will turn a turbine. And a turbine will turn a generator, which will make power. They're my electrical. Yeah, it doesn't look very good. Okay, so water is our primary mechanism. Geothermal energy exclusively uses water. So when we think about the site requirements or something that you need to use geothermal energy, well, firstly, we need our heat source. Secondly, we need water. Without either of these, you can't access geothermal energy. So you need large amounts of water to transport the heat, but you also need a heat source. Okay, we also need to think about locations. So we know that we need water and we need hot rocks. So those hot rocks could be anything from granite, but they could also be magma. So let's think about some places in the world where geothermal energy might be easily accessible. Remember, we need heat and we need water. So if we think about places like a divergent boundary, well, that's actually an ideal location. We've got magma rising to the surface, and often it's in areas where there's water. If we think about one location that is perfect, and that is Iceland. Iceland is located in the Atlantic Ocean on what's called the Mid-Atlantic Ridge. And they have magma that is just below the surface. Because they're also surrounded by the ocean, they have vast access to huge amounts of water. So they have heat and water that they need to access that. If we think about some other locations, divergent boundaries, you might think of the East African Rift. So that is the Rift Valley in Africa. Is it a location It's actually one that I don't know a lot about, but it seems to me like it would be a good idea. It's a divergent boundary. You would have magma rising to the surface. The only thing that you're missing, though, is water. So would it work? Sure. Convergent boundaries. Well, if we think about what we need heat and water in mountainous regions, so collision boundaries. We certainly have pressure, but do we have heat? It's probably at a depth that's far too deep for us to access, and also there's very little water. Subduction boundaries, they do have heat and water. So they're a location that might be useful. However, there is a great deal of hazards with this because there's volcanic and seismic activity in these zones. Transform boundaries. For me, it's a big no. There is no easy access to magma and heat, although there would be access to water, but generally I don't think it would be a location that would be as suitable as a divergent boundary. If we think about some other locations that aren't necessarily tectonic, you might also say a hot spot. And our most famous hotspot volcano is, I'm going to let you fill that one in there. So there's a location that is close to water and magma. Great, it's got it all. Also, anywhere where the crust is thin. So just like a delicious thin crust pizza, if we get thin crust, that allows us to access the heat. All right, so there's our locations. And if we think about plate tectonic movement, having our knowledge of plate tectonic movement and what happens at these boundaries, we can use that knowledge to make up decisions about whether geothermal energy is appropriate in an area. We might look at a divergent plate boundary and go, right, well, there we've got water and we've got magma close to the surface. That's a good location for geothermal energy. Or you might look at the San Andreas Fault and go, well, no, we've got no heat, we've got water, but we haven't got a lot of it. It's not really going to be a location that we would use. Perhaps you might think, okay, well, let's go the Himalayas. Would that be a good location? There's certainly a lot of pressure, but there's also a lot of seismic activity. And unless you're going to count the snow, there's not really a lot of access to large amounts of water. So it actually wouldn't be a great location. So our knowledge of this gives us the ability to make those decisions. We've also got to think about, so that would be, I guess, our environmental, but we've also got to think about economic and political decisions in whether to use this or not. And for example, in countries like Iceland and in our US state here, they certainly have the ability to use those resources because they've got the money. However, in Africa, do they have the finances to actually fund this sort of expensive geothermal energy activity? We could also look at places like Tibet, which is very seismically active. Would that be a suitable location? So we have to take all these things into account before we decide on whether geothermal energy is the right place, is the right type of energy to use in this area. Okay, in the next little lesson, we're going to talk about the 3 different types of geothermal energy, and that will be available later.